Hello and welcome to Wednesday's edition of Cracking the Cryptic, where we've got a colourful puzzle to have a go at today called the Fireflies Pairing Dance, and it's by Patrick Junke. And this has been recommended a lot to us, including, I might add, by Dying Flutchman, a very good judge of a puzzle and a very, very clever person indeed. So I'm looking forward to having a go at this. I did find it on Logic Master's, got some wonderful comments, and it's got quite an odd rule. The fireflies, which I think are the yellow ones, everything that has a dot, a yellow dot, the two digits have to be divisible by 4. So that could be 1 and that could be 7. Or that could be 3 and that could be 9. Or that could be 2 and that could be 6. And various other possibilities. So that is what we're going to have to do. Yeah, I'll read you the rules in a moment or two's time. And we'll have a look at the puzzle together. Now, what else do I have to tell you about today? Well, I don't have a great deal. We've had a request from one of our patrons, actually, for me to read a bit of poetry to you, which I'm always down for that. But I don't want to subject you to it too often. But I realise I have never read this poem on the channel before. I mean, partly because it's too long to read the whole thing. It's the Lovesong of Alfred Prufrock by T.S. Eliot, which is, it's a phenomenal poem. If you've never actually read it, and do have a look at the whole thing. It's quite stunning. It's sort of a meditation, I think, on aging. But I will read you a little bit of it, and you can castigate me as you like. And if by any miracle you actually want to hear the whole thing, which will be a lengthy read, let us know in the comments, and I'll put something on Patreon perhaps. But this is the start and end of the Lovesong of J. Alfred Prufrock by T.S. Eliot. Let us go then, you and I, when the evening is spread out against the sky, like a patient etherized upon a table. Let us go through certain half-deserted streets, the muttering retreats of restless nights in one-night cheap hotels and sawdust restaurants with oyster shells. Streets that follow like a tedious argument of insidious intent to lead you to an overwhelming question. Oh, do not ask, what is it? Let us go and make our visit. In the room the women come and go, talking of Michelangelo. No, I am not Prince Hamlet, nor was meant to be. Am an attendant lord, one that will do to swell a progress, start a scene or two, advise the prince, no doubt an easy tool, deferential, glad to be of use, politic, cautious and meticulous, full of high sentence, but a bit obtuse, at times indeed almost ridiculous, almost at times the fool. I grow old, I shall wear the bottoms of my trousers rolled. Shall I part my hair behind? Do I dare to eat a peach? I shall wear white flannel trousers and walk upon the beach. I have heard the mermaids singing, each to each. I do not think that they will sing to me. I have seen them riding seaward on the waves, combing the white hair of the waves blown back. When the wind blows the water white and black, we have lingered in the chambers of the sea, by sea-girls wreathed with seaweed red and brown, till human voices wake us and we drown. This incredible rhythm that poem has, I think, as well as the language, of course. Anyway, there we go. I'm sorry if you came here for the Sudoku, but you have to stay for the poetry. Anything else I can mention yes, have a look at this app. Oh, it's in the wrong place today. Goodness. This app, Cracking the Cryptic, Classic Volume 2. Loads of fantastic classic Sudoku puzzles, all handmade, all rather beautiful and exceptionally interesting. I guarantee it, and it's available on all platforms. Do also, our monthly competition is still a go-go until the 20th. Plenty of time left. Do have a look at that. You will enjoy it. And that, I think, is everything. Let's do some solving. Let's have a look at the Fireflies Pairing Dance by Patrick Junke. It's a good day to do poetry because that title is a bit poetic. The rules are as follows. We have got normal Sudoku rules apply, so we've got to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. A golden dot between two cells indicates that their sum is divisible by 4. So we've had a think about that already. I mean, actually, there are only a limited number of options given Sudoku digits, aren't there? I mean, we couldn't make those two add to 20, for example. 20 is divisible by 4, but it's not makeable with two Sudoku numbers. All possible golden dots are given. Okay, so that's a huge negative constraint. So that means it's simply impossible, for example, for that to be a 1 and that to be a 3. Because these should have a golden dot between them, and they don't. So I will almost certainly forget that instantly, but that is a rule. Golden dots take precedence over the black dots, i.e. if two cells could have a black dot and a golden dot, only the golden dot is shown. Right. I mean, it then goes on to tell us what a black dot is. It says a black dot between two digits indicates that one is double the other. So if we just think that through, well, so a black dot, let's do a black dot. If that was a 2, that could be a 4 because 4 is double 2, or it could be a 1 because 2 is double 1. But neither of those is divisible by 4. 3 and 6 are not divisible by 4. 4 and 8. Okay, so I think this rule is to deal with a very specific case. If you had a 4 and an 8, that domino would be divisible by 4, and therefore actually it would have a yellow dot between it. And as it's got a black dot, that's not a 4-8 pair. I think that's what we're being told. Not all possible black dots are given, so it's perfectly possible for this to be a 4 and this to be a 2. That would be completely legitimate. A white dot between two digits indicates they are consecutive, so that's sort of normal. If this is a 3, this is a 2 or a 4 in order to be consecutive with 3. Not all possible white dots are given, so again it's perfectly possible for those two to be consecutive. Just because there's no white dot doesn't mean that's not possible. Okay, and there's one more rule. It says the sum of two adjacent cells separated by a 3 by 3 box border are even. So those two, I was about to say, right, so that's going to put too many even digits in the grid. Of course it is not. It means those two, the sum of those two is even. So there's almost certainly going to be parity considerations that are going to crop up, I think, from that. So the sum of these two is even, the sum of those two is even. So every time that you get a 3 by 3 box border, the digits crossing it have to sum to an even number. Note that the sum of two adjacent cells not separated by a 3 by 3 box border may still be even. Okay, so it's totally fine for those two to be even. I'm gonna so forget which of these. Is it only the golden one that has a negative constraint then? I think it is. I think the rest of them are not subject to a negative constraint. Anyway, do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. So I'm not sure what we're meant to do here. I'm not sure whether I'm meant to do some sort of due diligence exercise to study to study how the golden dots work. I mean, in fact, let's just do that, because a golden dot, it's only got a few possibilities, hasn't it? It could add up to 4. 4 is divisible by 4, but only if it was a 1-3 pair. That's the only way that could work. It could add up to 8, but there's loads of ways of doing that. Well, there's 3. 1 7 2 6 3 5. So that's possible. It could add up to 12. Now I can't write 12 in big letters, but big numbers. So I could do 12 like that. Now that can be 5 7 4 8 or 3 9. Or it could add up to 16, and the only way 16 could work is 7 9, because getting 2 Sudoku numbers that have to be different to add up to 16 is relatively tricky. So 4 and 16 just have one option. 8 and 12 have 3 options each, and there are 8 options in total for how to generate a golden ticket, a golden dot. And how on earth is that useful? I don't know. I haven't got a clue. Okay, so I'm sorry. That's a little bit of due diligence that hasn't helped us at all, I don't think. So I wonder whether it's... Oh, hang on. Let me just go back to that. Yeah, maybe it's the parity thing then, because there's this funny rule about the box borders, isn't there? So the only thing I'm taking from the box border thing having to be even is that those 2 digits are the same parity. Because if this is odd, in order for that to sum to an even number, this would also have to be odd. So these are always having the same parity. And what that means, interestingly, is you're going to have a sort of these cells, which are sort of they're super constrained, aren't they? In the sense, if you got the parity of any one of those 4, it would force the whole 2x2 to be the same parity, because there are so many 3x3 box borders to cross. But yeah, okay, but because... Right, okay, so what I'm now thinking is the whole puzzle is about parity rather than particularly numbers being divisible by 4, because if we think about every single one of these options, because we're always adding up to an even number, because any number divisible by 4 will of its nature be even, because we're summing 2 numbers to an even number, the numbers across any golden dot are both going to be of the same parity. So I suspect what we have to do, this is now going to be proved wrong and I'm going to feel daft, is to argue I'm trying to see. So for example here, those 3 have to be the same parity, don't they? Because these 2 have to be the same parity because they're summing up to 4, 8, 12 or 16. Those 2 as well. So they share parity. But hang on. Hang on a moment. Right, so these are odd. Okay, I think these have to be odd, and I might be wrong about this. The way I've reached that conclusion is, having concluded they're all the same parity, let's just colour them just for a moment to indicate, am I just saying they're the same parity? Now, I know that to generate the numbers 4 and 16, I only use odd numbers to do that. So that's fine. You can use. But to generate 8 or 12, I can do it with even numbers, but only with 1. You know, there's only one pair that works for 8, and that's 2, 6. There's only one pair that works for 12, and that's 4, 8, and they have no digits in common. So if, for example, we decided, okay, that's 2, 6, this would be unfillable. because it would have to be another 2, 6 in order to... That's the only way that you could make this domino divisible by 4, would be to repeat the same 8 total. And the same is going to be true if we were doing 4s and 8s, isn't it? This would have to be another 4 or 8. So I think actually, I'm now going to delete this, and I'll probably go back again to it in a moment. But I think what we're basically being told is that this is odd. So, and that's going to be true everywhere that we get a triomino in a box. So for example here, that must also apply there, it must also apply there, it must also apply there. Yeah, but this is great, isn't it? Because surely now I can use that funny rule about crossing the yeah, this has got to be odd, that's got to be odd, those two have got to be odd. Because they're all crossing 3x3 box borders. Now this is good, I think. So now this has to be even, because if that was double odd, I'd have 6 odd digits in row 5, and there are only 5 odd digits in a Sudoku puzzle, 1, 3, 5, 7 and 9. So that's even, which means that this is even by the funny rule about crossing the box borders. Oh, these that's all forced, because these two are both touching these borders. I'm going to miss these, aren't I? I'm going to let me just think about this. That doesn't have to necessarily... Oh, that does have to be even. I was about to say that you could have opposite parities across a black dot, but I hadn't grokked in my mind that this was odd. You can't have 2 odd digits because one of these digits is double the other, so it can be written mathematically as 2 times x. Well, 2 times x is indisputably even. So that's got to be even, and this is odd, and this has to be 1 or 3 now, because if it was 5, 7 or 9, this would either be a non-integer or a non-Sudoku number like 10, 14 or 18. So this is 1 or 3, this is 2 or 6. And this is in this little coterie of 2x2-iness, so we can do that. Now, there must be at least 1 even digit on a black dot from the logic that we just did there. So there must be at least 1 even digit on the... that's really important. In fact, this is a bit like this. And the way I'm seeing that is weird. And forgive me. My sister tells me I've always been weird, and she's quite right. Okay, so the way I'm seeing that is actually looking at this white dot. Now this white dot definitely has because these digits are consecutive, one of these digits is even, and one of these digits is odd, and that means one of these 2 digits is even. But that's the 3rd even in this box, so this can't be a double even black dot, because there would be 5 evens in the box, and there's only 4 evens in Sudoku, 2, 4, 6 and 8. So this is one of each. I don't know the order. It'd be very useful if that was even, because then that would be a bit useful. Okay, but let's take an audit. So we've got even there, there's an even on there, there's an even in there. So those 2 are definitely odd, and that one's the useful one, because that's in the little 2x2 of 3x3 box borders. So that's got to be odd now as well. I've got all, there we go. I've got all my odds in the central box. This is really good. Oh, this is huge as well, because now these 2 are both even, so those 2 are both even, and this is another of these 2x2 funny things. Now I've got all my evens in columns 3 and 4, so all of those are odd. Yeah, this is great. Now this white dot comes into its own. There has to be an odd digit on it somewhere. And that's going to complete our complement of odd digits for box 2. So those are both even, which means that this is even. This is a golden ticket or whatever it's called, so that's got to be odd. Now, what do we do with that? is the question. And the answer is I don't know yet, but we can probably do something. Yeah, look at row 7. There's definitely an even digit on this white dot, and that's the 4th even in the row, so that's definitely odd. So the digit above it is definitely odd across the border. Now, okay, now I don't know what to do. Is this obvious? It probably is obvious, actually, because it's once you dig beneath the surface of this puzzle, actually there's quite a lot of information hidden away, isn't there? I can't see it. I've probably got a row or a column with the requisite number of evens or odds in it, and I just need to spot it. Oh, yeah, in fact, look at there it is, box 7. All of those have to be even now. I've got a horrible feeling that's not going to be useful because none of these are touching 3x3 box borders. We know that black dot is not 4, 8, don't we? Okay, yeah, let's think about that for a second. Because we know if it was 4, 8, it had to be a golden dot. Yet these are 2 even numbers. So they're not 4, 8. So they are 2, 4, aren't they? They can't be 3, 6. 3 isn't even. They can't be 1, 2. So, sorry, 2, 6. I was trying to type 2 and 4. So these 2 digits are 6 and 8. So 4 is in one of those 2 cells. If that was 4, that would be 6 because there's no golden dot across the border. Oh, that's an interesting point. Those 2 are both. Those 2 can't be 2 6s because they would make naughty dominoes that don't have golden dots but would sum to a number divisible by 4. Those have both got to be 4, 8. And that can't be 4, 8, so that's got to be 2, 6. Yeah, okay. So we needed to keep track, or I needed to keep better track of the fact that... Oh, wait a second, though. Hang on. Yeah, I needed to keep better track of the way that the even numbers interact with each other. Because in order to not make naughty dominoes, I can never put 2 and 6 together, and I can never put 4 and 8 together. So this domino, it depends what this is. If that's 8, that can't be 4. Well, obviously. But if that's 6, that can't be 2. Yeah, okay, let's look at the middle box actually, just for a moment. This domino here, if that was 2, 6, the puzzle would be broken because they would be a multiple of 4, they would add up to 8. So that's got to be a 2, 6, but that propagates. Now this one, this thing going across this boundary, this can't be 2, 6 now, so that's got to be 4, 8. And now this one has got the golden ticket, so that has to be a 4, 8. Now, what does that mean? I don't know. They can't both be 4, 8, because that would be naughty, so one of these is 2, 6. Okay. One of these is even. And the even digit on this white dot is a 4 or an 8. Because there must be a 2, 6 in this domino. Oh, bobbins, I don't know. Is it that one? Do I somehow know? I mean, if that was odd, that would be hugely powerful because everything else would be even in the column. That would be odd. So that would be odd. That would be odd. That would be even. This would be even. Oh, I thought I got a count on box 4, but no, I haven't. I'm one short on the odds. Right, okay, so how do you think we do this then? Do I have to, maybe I don't have to colour the grid. Maybe I've got to actually think harder about the possible pairings. Like this column here, I've got 2 good pairings to find, depending on what that is. So if that was 3, 1 would be on a domino. Now, what does that mean? One? Yeah, there is. Okay, here's a weird point. The way I'm seeing the bondings, that's exactly how I'm thinking about it. The bondings. So if you think about 1, what can 1 bond with to make a yellow firefly domino? 1 can bond with 3. 1 and 3 add up to 4. So then the moment you know 1 can bond with 3, you know 1 can bond with 7, because 7 is just 4 more than 3. So you've got to preserve that +4 relationship. So yeah, but that's okay, that doesn't work. Actually, not for that reason. But the problem with that is that 5 and 9 would be the leftover digits. And 5 and 9 add to 14, and that isn't 0 mod 4. Right. Actually, so this isn't... Actually, it's not then. Well, it was a bit about the even digits, but I think it's more about the odd digits. So... yeah, here you go. So how do you make a good, like a yellow dot compliant domino with the numbers 1, 5 and 9? The only way is with the digits 3 and the digit 7. Both 3 and 7 work for 1, 5 and 9. So yeah, so 1, 5 and 9 can never partner up with each other. Yeah, and that's why this column is important. Because if you do make this a 3, only one of these dominoes can contain a 3 or a 7. And you're going to need a 3 and a 7. You're going to need a 3 or a 7 in any yellow dot compliant domino. So this is a 1. I mean, that's quite tricky, but it is definitely right. Now, well, now that's a 2. I'm going to use that by the black dot logic. Actually, that's not doing anything. That's not doing anything. Can't believe it. Okay, so this has to be 3 or 7. Because we know that 1s, 5s and 9s always partner up with 3s, 5s and 7s to make things work. And therefore this is 5 or 9, because this is a 3 or a 7, so that's going to have to go with a 5 or a 9. Oh, right. Hang on. Because now this domino, and this domino actually, but this domino is not yellow dot compliant. So this cell... it has to be odd, because that's how we've coloured it. But it can't be 3 or 7, so that is a 5 or a 9. And now, here is a beautiful point. No, well, a bit. No, it is. This is huge. This is a huge issue. Because now, this cell I want to look at, that cannot be odd anymore. Because it would be the last odd digit in this box, and it would be a 3 or a 7, and that domino would be yellow dot compliant, and there's no yellow dot. So that is even, and that means we've got the count for this row. That's odd. That's on a black dot, so that's even. That's even. This is yellow, because that's a yellow dot. That's even. Now we've got an even below that, and an odd below that. Okay, well that was still good. It may not have been absolutely brilliant, but it was quite good, wasn't it? Okay, so these digits are now 2 and 6. So this digit is 1 or 3, and then we know what it is. It's 3. That's 6. That's 2. This is a really interesting puzzle, actually. Now this, because that's 3, it's sort of 3 and 7 are the magic yellow digit, the magic odd digits. They are, because they can partner up with all the 1s, 5s and 9s and make nice dominoes. So this has to be a 1, 5, 9. And it has to be a 1 by Sudoku. But now, oh, this is lovely. Look at this box. The 7 cannot go in this domino because it will partner up with a 5 or a 9 with it and make a correct total which should have a yellow dot. So the 7 has to be hidden away here. And this digit has to, and that digit's a 3 now. And 3 and 7 don't add up to 0 mod 4. This is beautiful. And now this is sort of a deadly pattern. What do I mean by that? Well, this digit here can't be 1, 5 or 9 because that would have a yellow dot. And it can't be 3 itself, so that's got to be 7, and that same logic applies there to this domino. So this sort of weird pattern gets unwound. Right, and these are now 1s, 5s and 9s, and you can see this is working here. There's no yellow dot, nor should there be. This is not a 1. I think that can be a lot of things. It's so mmany things, I'm not going to pencil mark it. What about that? That can't be a 2, can it? Because that would be a blue, that would be a yellow dot compliant blue domino, if such a thing exists. So that's a 4, 8. So we've got 4 and 8 as a pair in this row. Two by Sudoku is that cell. So one of these is a 6, which means this is a 6 by Sudoku. So this is this is huge. So this is a 4 or an 8. But once this is a 4 or an 8, what's this? It can't be 8, because that would be a good domino that should have a yellow dot. So that's got to be a 6. That's got to be an 8 in the corner. It almost deserves a song, I think. This domino cannot be, there's no yellow dot, so it's got to be a 2. That's got to be a 4. So, oh no, it doesn't quite work. There's no yellow dot there, so this is a 4 or an 8. And so this digit is a 2 or a 6, and it's not a 2. So that's a 6. This is a 4 or an 8. There's no yellow dot here, so this is a 2, because it can't be a 6. This is a 4 or an 8. Oh, bobbins, and both of those work on that white dot. Oh, this yellow dot can't be even, because there'd be 5 evens in the column, so that's yellow, which means this is even. Now, well, yeah, these are the same parity. If both of those are orange, we've got 6 oranges in the row, so they are both even. This is odd. I've got 5 odds, sorry, in box 9, so those are both even, which makes that even. Now I've got all my evens in the bottom row, so that's odd. Let's have a look at this column. I've got all my odds, so that's even. That's on a white dot, so this is odd, and it goes across the boundary. Oh, come on, that's rotten. Is this not... Oh dear, That looks a really dodgy domino. How am I going to get that fixed? Okay, I don't know. Now, something's going on here as well, isn't it? But what? How do we do this? Yeah, this cell is not capable of being even anymore. It's got 2, 6, 4 and 8 looking at it, so that's got to be odd. That's got to be odd. This is now in this row, we haven't got enough evens, so that's even. That's even. Still in a bit of trouble, I think. We've got these white spaces that I don't really understand how I'm ever going to colour them, but I'm sure it will be revealed. I just don't understand it immediately. Now this is going to have to be 3 or 7 because there is no yellow dot across that boundary, and we know there must be a 3 or a 7 on a correct. Oh, in fact, I know where it is. It's got to be there because this can't be 3 or 7. So this is a 1, 5, 9. And these are 1, 5, 9, and this is on a correct one, so that's got to be with a 3, 7. Now this cell is also a 1, 5, 9, so that's got to be a 3 or a 7. Oh no, hang on, careful, there's no yellow dot, that's absolute nonsense. That's got to be a 1, 5 or a 9. This has got to be a 1, 5 or 9, so that's got to be a 3 or a 7. So this has got to be a 1, 5, 9. This 3 means that is a 7 actually, so that's a 3, that's a 7, that's a 3, that's a 7. It's a brilliant idea actually, this. Where's 1 in row 4? It can only go there. And there's no naughtiness. Oh, these are 5. This is a 5, 9 pair. Sorry, that's totally obvious to everybody. I just didn't see it. In this column, we need a 1 in one of those, so that isn't a 1. I've now got a 5, 9 in this row, so this is a 1. And this is a 3 by Sudoku, because that 3 has to find a home. So 3 is now in one of those 2 cells by Sudoku. 7 is in one of these 2 cells. This digit down here is a 5 or a 9. And I've got to put a 1 on this dot along with a 7. And 1 and 7 add up to 8. And 8 is 0 mod 4. So that sort of makes sense. It's just not quite. We're not quite getting this final pattern at the top done. 2 by Sudoku has to go there. Yeah, that's a 6, therefore. Same sort of principle. This is a 4 or an 8. It's going to have to be the white dots, I think, that resolve how we do the 4s and the 8s and the 2s. And maybe the 2s and 6s will resolve. Nah, nearly. Where's no? I thought I could do something then. Okay. Yeah, where's 2? This is a big point actually. Where's 2 in box 1? It can't go next to 6, can it? That domino would be a compliant domino and it should have a dot. So the 2 goes here, which makes that the 3, but that therefore is even. That completes the evens for this column, so that's odd. Oh no, it's still not, that's still not enough. Okay, so these are 1, 5, 9. This can't be 1, 5, 9 because that would be a compliant domino. So the other of 1, 5, 9 must hide in the corner, making this digit 4 or 8 an even. And hopefully now, yeah, we've got all our evens in this row, so that becomes odd. That becomes even. Now, this digit in the corner sees 2 and 6. So that's got to be 4 or 8. These have got to be 2 and 6, and we know the order. So 2, 6, 7 using our pencil mark unwinding. 7, oh, that's okay. 3 and 7 are okay across the boundary. I thought I made a ricket. But we're still good. We're still good. Now, how do we finish this off? I feel like, yeah, 2s must be virtually done, mustn't they? How many 2s have I got in this grid? all of them. How many 6s? Several. Yeah, where's 6 in this box? It's in this domino. So 6 is placed. And we could have done that a different way. We could have done it by considering that if this is a 4-8, it would have partnered up in a naughty way in one direction or the other in a sort of Harry Styles manner with another 4-8 and made a yellow dot compliant domino, and it didn't. So this is 4-8. That's this white dot stuff it's not resolving yet. 6 is in one of these cells. And this is a 5 or a 9. Yeah, we're going to need a 3 on this domino down here for it to work. And we're going to need, whoopsie, if the 3 was here, this would have to be a 7. And it couldn't be in order to make two dottednesses. So that's a 3. These are both 1, 5, 9 digits, as is that one actually. The 1 in the column is in this domino here, so this isn't a 1. And now the 1 in column 4 has to be there. Oh, it's just ridiculous. This is now a 5 or a 9. This is a 1 by Sudoku. And we're going to have to play that same game, I think, in these cells, aren't we? Well, actually, yeah, we've got 3 and 7 left to place, and this is all white dotted loveliness. Sorry, orange dot. No, yellow dotted loveliness. So we're going to have to separate the 3 and the 7, and that's going to require them to be in this order with a 1, 5 or 9 between them. And now that means this is 7, this is 1, and oh, this is 1 by Sudoku because we have a 5, 9 pair here. I feel like I've done a lot of 1-edges. I've done all my 1s, all the 3s, yep, all the 7s. Yes. So something... There's got to be some way of resolving this. How are we going to do it? I'm sure you've all spotted it. I haven't seen it yet, though. That is a compliant domino, so that's allowed to have a yellow dot. Oh, this 4, right? That is gonna go through the grid like you know what, isn't it? That really is. Yeah, 8, 4, 4, 8, 4, 8. Yeah, 4. Oh, that's gonna do this one. That's great. It's a beautiful puzzle. It is. I mean, that's all you can say about it. It's really clever. Now look across here. This has to be 5 to make the white dot work. And that hopefully is going to keep going. Yeah, this is doing stuff. Oh, no, it still is. It still is. Okay, we might need... Oh, we've got the 4 here. So this top section of 5 9s is also getting resolved in the same manner. Okay, and then all I've got to do is figure out the bottom bit. Well, I can put 4 in here. 4, 6... 6, 8, and there the puzzle suddenly solved itself. We didn't have to do anything. That was fabulous, really interesting, really very novel. In all of the best ways. Patrick, take a bow about that one. Let's see if this must be right. Oh, hang on. Solve counter 1. I can't be the first person to solve this puzzle. It's been on Logic Masters. Congratulations, you've guided every glowing pair through their dance. The testers must have... they must have changed something about it to make it... I don't know. I don't actually know what's happened there. I don't think I am the first person to solve this puzzle. I think it's been around for a while. But anyway, it says we got it right, and that's important. And it was absolutely magnificent, and I enjoyed it immensely. Do let me know in the comments how you got on. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.